Neural networks using matrices and vectors. So far we have been using scalars to design neural networks. So in this video, we will be using neural networks using matrices and vectors. The process and method, everything will be same, but instead of using scalars, we will use matrices and vectors. So let us assume that we want to estimate a function. Let's say there is a function y equal to f of x1, x2. Let's say we have two inputs and one output, and what is known to us, we know inputs and output, but we don't know this function. So our goal is to estimate this using neural networks and obtain a criteria like this, so it can estimate this function. So I have already drawn this diagram. So we have inputs x1, x2, so there are 4 neurons, and we have a output y of t, right? The number of neurons can be increased. Let's say we have n number of neurons. Okay, let's do it for a general case. So we have n number of neurons, so we can define, okay, before that let me tell you the steps for each neuron. We already know this, that the first step is to do linear combination, and the second one is to do activation. Okay, so let's define an input. We have two inputs, so let's define a vector x with two inputs x1 and x2, right? So we know that for each neuron we have two operations, right? So in vector form, what we are going to do is, I have already written this, but I want to explain it to you because we will be noticing the dimensions of each vector or matrix. So the first step is z is equal to wx plus b. So if you recall, z contains the linear combinations of each neuron. So this z is also a vector. So z1, for this case we have 4 neurons, so it will be z1, z2, z3, z4, and if there are n number of neurons, let's say there are so many neurons over here, so this will extend to n, because linear combination is performed for each neuron, so this will depend on the number of neurons. X, we already defined this, its dimension is n. We can write it as a small n, which is equal to 2. Dimension of Z matrix, this is capital N, which represents number of neurons. Similarly, B is added to each linear combination, so this is also a vector. It will be a vector like this, b1, b2, till the number of neurons, right? So the dimension of B matrix are also capital N. Okay, now the key point in this lecture is, what is the dimension of this W? Is it a matrix or is it a vector? So W is actually a vector. So just to give you a brief recall, or let's recall the previous concept. So previously we calculated z1 is equal to w11 x1 plus w12 x2, right? So z2 w21 x1 plus w22 x2. So if we write this in vector form, this will be z1 z2, right? And we already wrote this, that x is a vector. So what we will be left over here, it will be w11 w12, because when we multiply this we will obtain this equation, w1 x1 plus w12 x2, right? Similarly w21 and w22. So W is a matrix with dimension 2 cross 2. But for this case, we had two inputs and two neurons. So that's why this was a square matrix. Actually, what happens is that W has a dimension of n cross small n, right? So this represents neuron, this represents number of inputs. So for this case, let's say we have 4 neurons. So W will be 4 cross 2 because 4 neurons, 2 inputs. Okay. Now after that, the next step is same as before. We have to do the activation. We already know this, that activation is performed by passing the linear combination through a activation function, and we were using sigmoid function. So this will become 1 plus e power minus z. Now this is really important because when we take its derivative for gradient descent, we will see this in next slides. So we have to note the dimension of h. So this is the dimension of h. So its dimension also depends on the dimension of z. So what was the dimension of z? It was n. Okay, so just remember this. So as always, we perform 2 steps. After that, what we are going to do is we are going to define the error, but error is y minus y hat. So before that, what we have to do, we have to finalize the estimated function. So the third step is estimated function. We already calculated this previously, if you recall, right? So we can also write this as this phi of x was actually this h. So let me write it in capital alphabet, and we can also add bias to the output. Okay, this, why do we add bias to the outputs? We have already discussed this in one video. You can go back to that video and see why we add this bias. So what are the dimensions of V? The dimension of V, they also depend on number of neurons. If you recall, each neuron is connected to the output, right? So if we have 4 neurons, so we will have V1, V2, V3 and V4. So this also depends on the number of neuron. And what is B bar? This is actually a constant. It will be just a real number in this case, because when we multiply this V transpose into H, this will be also a scalar number, right? So V hat will be scalar, and this is actually what we need because we have one output which was also a real number. So after that, the next step is to derive error y minus y hat, and our goal is to minimize this error. So how do we minimize this error? If you have watched previous videos, so it is really easy. The step is to define a loss function. Loss function j is equal to half e square. Okay, and after that we have to find the gradients of each weight. So we have w, we have v, we have bias in the input weights with the input weights, and we have bias with the output weights. So with respect to these variables, or should I say constants, these will be variable because with each iteration w will change, v will also change, all of these values will change. So we have to differentiate loss function with respect to these to obtain a criteria such that e approaches to 0. So let's do the gradient descent using the output weight. This is really easy because we saw this in the scalar case as well, because the output y, this directly gives us e and j, and it was easy to compute the derivative. So let's go directly into the output derivative, and then we will go back to the derivative with respect to w, which was a bit complicated. Not complicated, but it was a bit lengthy. So let's derive this first. So we know this, that dv what is j? J is actually 1 by 2 e square. And what is e? E is actually this value, right? Y minus y hat. So I can write it like this, y minus y hat square, right? Now I will simply derivate it. So I will obtain 1 by 2, same as this, 2 y minus y hat, and then derivative of inside function, which is inside. So derivative of y with respect to dv, this will be 0. Derivative of y hat with respect to dv, this will not be 0 because y hat is dependent on this function, right? So we have this v transpose. So what we will obtain here is that this v transpose will vanish due to this differential term, and we will be left only with h, right? So this becomes, now y minus y hat, this is e and this is minus h. So dj by dv is equal to minus e h, right? Really simple. Similarly, let me do it directly over here. When we obtain the derivative of loss function j, dj by db bar. So when we reach this point, this will be same as this 1 by 2 y minus y hat. When we reach this point, here we will take derivative of y with respect to b bar, so it will be 0. Then derivative of y hat with respect to b bar. So in that case, this v transpose h will be 0 because v bar does not appear here. So we will be only left with derivative of b bar with respect to b bar. Derivative of b bar with respect to b bar, so this is 1. So what we will get here is e times minus 1. So derivative of loss function with respect to b bar is equal to minus e. So these were the gradient derivations of output layer. Next, we have to derive the derivative with respect to w and its bias b. So that is a bit lengthy. Let's go to the next slide. So even if it is lengthy, it is not difficult, because if you recall, we designed a criteria using some chain rule, which made it really simple for us. So we will discuss that criteria once again. Now we have to derive the gradient with respect to the input weights. But the issue we faced in the scalar case was that w did not appear directly in this loss function. Loss function was half e square. It was dependent on y hat, right? Because j was dependent on e was dependent on y hat, and y hat was obtained using sigmoids, right? Then we had this linear combination, and then we had input. Just I want to recall once more, we had inputs x1, so we using weights w11 we obtained z1, we also had w12, right? Then we obtained h1. After that we obtained, this was using sigmoids, right? So this is the same setup. After that, what we obtained, we obtained y hat, then error, and then loss function. So same process will be used over here for vectors. So using weights, we can obtain linear combination, then we can perform activation, then we can perform a mathematical derivation to obtain y hat, then e, and then j. This is the same step like the scalar case, but using matrices and vectors. So now to derive this derivative, what we can do is we can use chain rule. Okay, so what does chain rules say? We can derive derivative of j with respect to e multiplied by derivative of e with respect to y hat, right? derivative of y hat with respect to this activation, derivative of activation with respect to z, right? Derivative of z with respect to weights. So if you look closely, all of these cancels out. Then left hand side becomes right hand side. Okay? So now we can easily derive these derivatives. It's really easy. Because I have, let's do this first one. So I know this, let me call it a. What is j? J is half e square, right? This. So derivative of half e square with respect to dE. So this is really easy. Half 2 times of e, derivative of the function inside this, so it is 1. So derivative of loss function with respect to e is 1. Really easy, right? Now derivative of error with respect to y hat, again this is very easy. Let's do it over here. Derivative of e with respect to y hat, so we know this, that error is y minus y hat, so this becomes 0 minus y hat, derivative with respect to dy hat, so dE by dy hat, this becomes minus 1, right? It's really easy. But the key point will be the derivative of sigmoid function, but we have not reached that point yet. So let's do the derivative of dy hat with respect to this derivative of sigmoid. Let's go to the next slide. Dy hat with respect to d sigma. Okay, so I will write it directly here. The third one is dy hat with respect to sigma. The third one was dy hat with respect to d sigma. Now this is also easy because I know this, that what is y hat? Y hat is actually the output v transpose h, right? And what is h? H is actually sigma of z. So I can write this as d sigma y transpose sigma of z. Now I have two terms, v transpose and sigma of z. So when I derivate it, this is actually also sigma of z. So when I derivate this, so I will directly obtain the values dy hat by d sigma of z is equal to v. Okay, really simple. Now the next one is derivative of d sigma, but with respect to dz. So we already calculated this derivative, and we also have one video how to derive the derivative of activation function. So we derived this 1 minus sigma of z. So this is valid for both scalar case as well as vector case. But the key point here is that we have to note its dimensions. So sigma of z is actually a vector, okay? A vector with dimension this, right? So 1 minus, this is also a vector with dimension this, okay? So how do we derive this? So the problem is that when we derive its derivative, this will be obtained as diagonal matrix. So if let's say for first sigmoid it will be sigma 1 minus sigma 1, right? Then for the second one it will be sigma 2 1 minus sigma 2, and so on, sigma n minus sigma n. So this will be actually a square matrix because we are talking about diagonals. So for two inputs and two neurons, the dimension will be R2 cross 2. Okay, and here we saw that the dimension was a vector dimension. So for two neurons it will be 2 cross 1, or for n neurons n cross 1. keep this in mind, because when we will be doing the multiplication to obtain dj by dw, these two are really key for matching the dimensions of left hand side and right hand side. Let's do the last one. The last one was the derivative of z with respect to derivative of w, right? So derivative of z with respect to w. So we know this. What was w? It was wx plus b, right? Now sorry, now derivating it with respect to w, so this will be 0 and we will obtain x dz by dw, but this will be x transpose. Let me explain it to you why. If you recall, we had z1 is equal to w11 x1 plus w12 x2, z2 is equal to w21 x1 plus w22 x2. So when we derivate this with respect to the weights, we obtain derivative of z1 with respect to the weights, right? So we will obtain x1 and x2 in this form, right? So this is actually the transpose of x, because if you recall, we had x is equal to x1 and x2. So to write it in this form, this will be transpose. So now we have all the values. So we will simply put these values to obtain the final equation. So how we can do that? Let's go to the next slide. Now let's rewrite the equation for the derivative of loss function with respect to w. It was, right, with respect to dy hat, derivative of phi hat with respect to sigma, derivative of sigma with respect to z, derivative of z with respect to w. So we derived this dj by de as e, right? This was -1. Let me see. Yes, this was -1. And dy hat by d sigma, this was v. This was a derivative like this, sigma z 1 minus sigma derivative of activation function, right? And this was x transpose. So we obtain minus e v sigma z 1 minus sigma z and x transpose. So this is the final equation. Just to match the dimensions, so weight was actually for the 2 inputs and 2 neuron case. Let's say weight was, let me draw it here so you can understand it much better. We had 4 weights, 2 output weights. Okay, so let's say, so here for this case w dimension was 2 cross 2. So we want to find this dimension and match with the right hand side. So the dimension of e, what is the dimension of e? We already know this, right? E is y minus y hat, right? So the dimension of e will be 1 cross 1. It will be a real number because y is a scalar output, so it will be a real number. 1 cross 1. Now what was v? V was a vector, 2 cross 1. Now what was this sigmoid function? This was also 2 cross 1, and this will also result in 2 cross 1. And we have this vector x was 2 cross 1, but since this is a transpose, so this will be 1 cross 2. Now you might be thinking that these multiplication are not possible, right? So in this case, what we will do, we will use a special multiplication in which we do element wise multiplication, right? I will explain it to you. So this will become 1 cross 1. So when we do element wise multiplication, this whole multiplication will become 2 cross 1, and then this 1 cross 2. So this will as a whole will become 1 cross 1 multiplied by 2 cross 2. So since this is a scalar, so we will obtain 2 cross 2 result, which matches the left hand side. Now the question is how to perform this multiplication. So this is actually really simple. So let's say we have two outputs in this case, v1, v2, right? So we will have v1, v2. Now for this case, sigma of z, we have h1, h2, right? And for this 1 minus sigma, so this will again be 1 minus h1, 1 minus h2, right? So what we are going to do is that we are going to multiply element wise. So this will be v1 times h1 times 1 minus h1. Okay, so we get the first row. Then the second row will be v2 times h2 times 1 minus h2. So we get a vector which belongs to 2 cross 1. Okay, so we obtained dj by dv using this equation. Now these are gradient descent criteria, right? But this is not the end. After that we have to update our weights. So how we will do that? So let's go to the next slide. If you recall, we had to define weights using a criteria. We had this criteria, if you recall, from the scalar case, the gradient descent criteria, to adjust any weights. This was a general formula, if you remember, theta new, theta old minus eta dj by d theta, right? So using this criteria, we will update our weights. So w new will be w old, which we use as an initial, the value of w old was given to the neural network at the beginning when we initialize the network, then eta, and then we have dj by dw. So we already calculated this in the previous slide, and eta is a constant used for tuning the approximation, so it is a constant. And then similarly we can update our v new, v old minus, this is minus, looks very big but it is minus, dj by dv. Similarly, if we have the output biases and we want to train that as well, so b bar new is equal to b bar old, this is the output one, eta dj by db bar. We calculated all these three parameters. I didn't calculate the loss function derivative with respect to the input bias, but its process is same. We have to apply a chain rule and derive this, okay, because we know that z is equal to wx plus b. From this we obtain h, then we obtain activation function, which is actually the same one, then we obtain y hat, and then e, and then j. So this is the same process. We have to derivate it until we get the derivative of this one. But nonetheless, how we obtain the criteria for this, which is the gradient descent, is equal to b old minus eta dj by db. Okay, so these four criteria update our loss. So what we know in the beginning of a neural network, this is just a summary. We know output and inputs, but we don't know the function x2. It can be any function, we don't know this. Okay, so to start neural network, what we do is we perform linear combination and activation, but for linear combination we need weights. So what we do, we initialize these weights these was for input, these were for input. We initialize, we give them some random values, and then neural network starts working on it, and it computes error and try to minimize the error or reach zero value, so it converges to zero, and after that we obtain our estimated value after I don't know how many iterations. It could take 10 iterations or maybe 1000 iterations, and then we obtain our VT hat, VT into H, which is sigmoid plus B bar. So once we approach, once the error approaches zero, this y function, estimated y function, becomes y. We will see its programming in the upcoming videos, and we will see that it estimates the function accurately, but it depends on eta, which we have to tune. So usually we use its value between 0 and 0.5. It is good range, but sometimes we have to increase this range. So this was the neural network using matrices. I hope you understood all this concept. It is based on the same concepts which we did for scalar. For scalar's case, we did it in more detail, and here I did it directly because the concepts were same. But for scalar and matrices case, we have to be careful about the dimensions of matrices and vectors, because if we cannot match the dimensions, the multiplication will not happen and we will get error in programming. One of the key point was the dimensions of sigmoid derivative. So remember that there we have to do the multiplication using element wise, and we can match the left hand side and right hand side dimensions, and hopefully we will obtain our estimated function. So that's all for this video. Thank you.